All right, you guys. So for number 5, and this is a quick heads up, the lines of math you have to do are not that hard. But what is really hard is to understand why you're doing what you're doing, the context, and the procedure. So this is just a quick heads up. There's going to be a lot of talking. There's going to be a monologue. And if you really want to understand everything, you got to sit through it from beginning to end. All right, so I'm just saying this is a hard problem in terms of understanding the concepts, but the lines of math are not that crazy, okay? And so I'm just saying, you guys, like, understanding the context in this example in particular is very important. So if it gets confusing, don't worry, this is a confusing problem, okay? This is a challenge. I'm just letting you know. Enough blah blah, let's get into it. So for number 5, we have that a company manufactures metal tubes for bicycle frames. All right, cool. The diameters of the tubes, d millimeters, are normally distributed. So this is my first big hint, are normally distributed with a mean 32 and some standard deviation. Then the other big hint is that the interquartile range of the diameters is 0.28. And through all of this, you need to find the value of your standard deviation. Now, unless you have the tools at hand and have the procedure very clear, you probably have no idea what to do, okay? And that's okay because this exercise is very specific and I've actually realized that they really like to ask this, okay? They really like to ask this in different ways, but at the end of the day, what you're gonna end up doing is taking the distribution they give you and standardizing it, okay? Now, I'm going to eventually reach what standardizing means, what it does, and etc. But this is just a heads up, that is where we're going, okay? And so, first things first, what is a normal distribution? So, a normal distribution looks something like a bell curve, okay? It's also called a bell curve. And the cool thing about the normal distribution, if anything, is that it actually shows up a lot in real life. For example, if you look at the weights of all newborn babies and you draw a line, right? And this is going to be like, I don't know, like quantity. And down here it's going to be weight. You're going to discover a normal distribution. And the cool thing about the normal distribution is that it's perfectly symmetrical and it's always the same. And so if you take the weight of enough newborn babies, you're going to end up with something like this, where down the middle you have your mean, and like 1 over to the left, it's going to be the mean minus the standard deviation. 1 over to the right, it's going to be the mean plus the standard deviation, and so on and so forth. Now, why is this useful? It's useful because this normal distribution is very familiar. You can use a bunch of tools associated to it because it's something that repeats a lot. The other thing that's nice, because it's symmetrical, is that if you discover, for example, this side of the diagram, then you can flip it over to the other side, right? And you also find this side of the diagram. So the main idea I'm trying to tell you here is that the normal distribution, thankfully, is symmetrical. Okay, it's symmetrical, it's familiar, you can use a lot of different tools that go along with it, okay? And so, let's go ahead and plug in the information we have into a normal distribution diagram. And so, what you know up until now is that your normal distribution has a mean of 32, so right down the middle. The mean is always going to be right in the middle for normal distribution. Right down the middle, you have a mean of 32. You have a standard deviation that you don't know, so your parameters are of a normal distribution 32, comma, just some standard deviation, and the interquartile range of the diameters is 0.28. And there, ladies and gentlemen, is the big step forward that we have to take. So first thing first, or second thing second, because I already said that. What is the interquartile range? So there's two types of ranges that you might have heard before. On the one hand, you have the range, and actually let me explain this by doing a box and whisker diagram, see, because this is usually how it gets explained. So I'm just going to try to keep it friendly, see? So over here, you can have like a box and whisker. Actually, yeah, I'll put a line here, it's fine. And so a box and whisker, basically, you have like 5 key points, right? On the one hand, you have your minimum, you have your maximum, you have Q1, you have Q3, and you have Q2, which is also called the median, okay? So your data can be expressed in a box and whisker, okay? And the box and whisker, why am I bringing it up? I bring it up because it's very useful in order to explain what interquartile range means. And so as I was saying, you have two like types of ranges. You have the range, which is like the normal one, and then you have the interquartile range. Now, the range is just going to be max minus min. So it's just going to be this guy minus this guy, right? While the IQR is actually Q3 minus Q1. And so it's actually this guy, this guy minus this guy, see? And so visually, it can actually be very appealing. And so like the range is like of the whole thing, right? And the IQR is of your inner data. Now, why would you ever want to do that? Well, you might want to do that because you're more interested in the middle of your data. You're more interested in the majority of your cases, right? And so that is why you would maybe consider the IQR more than the range, because this in the middle is the majority of your cases. Now, how do you know it's the majority of your cases? Well, because Q3 and Q1 and all these Qs, why are they even called Qs? They're called Qs because they make reference to what we call quartiles. And so quartiles, as you can see in quarts, so like in fourths, right? So Q1 is going to be the 25th. Actually, yeah, I'm going to do 25th percentile of your data. And so your Q1, for example, is like the person number 25th on your data, if it's 100 people, see? Q2 is the 50th percentile, so it's right down the middle. And technically Q3 is going to be your 75th percentile. And so why is it worth looking at it like this? Because now if I add on to you the information that the minimum is like the first one, right? Technically, the first person on your list, while the maximum is of course the 100th, so the last person on your list. Well, now you can maybe further understand that because Q1 is the 25th and because Q3 is the 75th, technically, if this is 25% and this is 75%, right? The the IQR with Q3 minus Q1 is giving you the middle 50% of your data. It's giving you the middle 50% of your data. That is like the big sort of idea of the IQR. It gives you the middle 50% of your data. It's the most key points probably that you want to analyze. So that is why the IQR exists in the first place. And how can you express that over here? Well, they tell you that the interquartile range of the diameters is 0.28. And so basically IQR, which is Q3 minus Q1, equals 0.28. And so what's happening here, right, is that if you take 25% of the left, right, so it's going to be 25% here, and then 25% of the right, all that distance is going to be 0.28. And so if all this distance is 0.28, that means that just to the left, right, just to the left, it's going to be 0.28 divided by 2. So it's 0.14. So just to the left, you're moving 0.14, and just to the right, you're moving 0.14. So that means if you take 32, right, if you take 32 and you subtract from it 0.14, you just discovered that this number here is 31.86, and that to the right, you take this 32 and you add 0.14, you end up with 32.14. And this, ladies and gentlemen, is actually huge. So what you just discovered is that Q1 is 31.86 and Q3, right, is 32.14. That is what you just discovered, and this is what you just express onto your diagram. Now from here, we still need to find the value of the standard deviation, right? But we did make big process in understanding what they were giving us, how it looks in a diagram, blah, 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 blah. And here's the big sort of jump in concepts that we have to make. This is probably going to be the hardest part for us to understand, so get ready. By standardizing it, you can reach the standard deviation. And there's a couple different ways to explain this. See? The most straightforward way that I'm going to tell you is the following. If you go to your formula booklet, and it's very important that you get familiar with it, because the day of the test, you're walking in with 2 years of experience, 2 hours of sleep, a whole lot of motivation to do well, your graphing calculator for paper 2, and a lot of motivation and yada yada. you also walk in with the formula booklet. So get familiar with the formula booklet. It is filled with tools that you can use the day of the test, and don't, like, get confident in the fact that I'm walking in with the formula booklet so I can just use it. Study with it. Know what's in it. There's a lot inside of it, and what use is having the formulas if you don't know what they have or what they say? Okay? And so that kind of stuff is very important to, like, just study with the formula booklet. Okay? Stick with it. It's gonna save your ass. For real. Not even kidding. So, anyways, eventually you're gonna find that for statistics and probability, well, on the one hand, I forgot to mention the interquartile range is here. So if you ever forget what it is, boom, there it is. So look at that, useful to know. And also, if you keep scrolling, here's the standardized normal variable. Now, why am I bringing this up? Because in your formula booklet, and this is huge, in your formula booklet, the only place where you have the standard deviation, unless you're HL, which we're not going to talk about today, the only place where you have standardized deviation is here. And so this is the formula you can use in order to find standard deviation. And so let me just write down that equation over here. And so z equals x minus mean divided by standard deviation. So if you are able to find the z, the x, and the u, you can just get standard deviation alone, and bada bim, bada boom, you find the value of your standard deviation. And we're way closer than what you think. But now I need to explain what the heck standardizing even does. What is your z value? Blah, blah, blah. So, first things first. The standardized normal, right? Because when you, how can I say this? So, technically, okay, this diagram that you did here, all right, let me redraw it up over here, right? So this diagram that you did here, which we said that this is 32, that 25% to the left, you find 31.86, and that 25% to the right, you're going to find 32.14. This is a normal distribution, right, with a mean of 32 and some standard deviation. And technically, if you standardize this, what you end up with, and this is the cool thing about standardizing, okay, what you end up with, like for real, once you standardize, you end up with a normal distribution that has a mean of 0 and a standard deviation of 1. And this is massive. And I know I'm just a guy on the internet that's a little bit of a nerd with math, but this is actually massive because once you standardize, you end up, and this is the key idea, you end up with a normal distribution whose parameters you know. And this is huge. Every time you standardize, you end up with a normal distribution with parameters mean equals 0 and standard deviation equals 1. Every single time you standardize, you end up with these parameters. And so it's very like familiar land, okay? Familiar, it's a familiar space. See, so once you standardize, you end up with a very familiar space. It's always going to be a mean of 0 and always going to be standard deviation of 1. Now, one of the first ideas I said earlier is that every single normal distribution has like its equivalent in a standardized world. So let me say that again. Every single normal distribution, you can sort of like change the numbers a little bit, but the proportions are the same, right? The proportions are the same, and you end up with its standardized version. And so how would that look like? Well, think about it like this. And so you know that the mean over here is going to be 0. And so instead of 32, right, now our mean is 0. And if you go 25% to the left, right, here is some value, and that is why they call it z. Here is some value which we will call z1, okay, because technically there is a z2 over here if you wanted to do it that way. So technically there is two z values, right? And so z1 equals its equivalent of 31.86, and z2 equals its equivalent of 32.14. Okay, that is what's happening. Like these z values are its equivalent in the original, right? And so z1 because of proportions, they both have 25% going to the left from the middle. Z1 is going to be 31.86. And so why am I saying this? Because the moment you find Z1, you're one step closer to plugging in these three values. Now, I talked about Z, that is your Z value. See, it's like the equivalent of the original in the standardized version. Your X is actually the value of the original. And so in this case, our approach is going to be saying that X is this guy here, and that, well, Z is whatever Z1, which I'll explain in a moment how to get it. And the mean, well, you already know the mean from the problem. The mean is 32, see? And so, boom. Now once I find Z, I can plug all of that over here, see? So, just a quick review. The Z value is the equivalent of the original in its standardized form, okay? The mean is still going to be the original mean, and the X is the value of the original one, okay? Now, how can you find the Z value from here? All right, here you need to get at least a little bit creative, see? And so because it's a normal distribution, the main tools you have are three. So if you actually go to your graphing calculator and you go to second vars, so you hit distribute, you have three main tools, which are the first three. You have normal PDF, normal CDF, and inventory normal. Now, you can go through them yourself, but intuitively I will put it like this. Normal PDF is basically going to be for finding the probability of landing one number, see? And so you put in the X value of one number and it's like, yo, what's the probability of getting just this guy, see? Normal CDF, it's going to be finding the probability of landing a specific interval. And inverse normal is basically finding the X value given a probability, okay? And so let me just explain this visually really quick, see? So if you have a normal distribution, normal PDF would be something like this. Normal PDF would be, what is the probability of getting just this guy here? See? So just this sliver of area, what's the probability of getting this? Normal CDF, that's here in green, is basically like, what's the area of landing between this lower bound and this upper bound? What's the probability of landing this area? See? That is what normal CDF is asking for. And inverse normal is basically like, yo, this is my area. What is my X? Okay? What is this X value? See? So inverse normal reads left to right. And so, this got kind of interesting, didn't it? And so from here, you can try to find, right, this area here. And so once you find this area here, you can do the equivalent over there, and it can help you find a Z value. And so technically from here, you can do inverse normal of 0.25. Now, why would I do an area of 0.25? Because if you look over here on my graph on the right, well, you already said that you have the middle 50% because of your IQR. And so that actually means, and I forgot to mention this, oops, but it's key now, so I'm going to say it now. That actually means that this remaining side over here is the upper 25%, and this remaining side over here is the lower 25%. So if you use inverse normal of 0.25, a mean of 0, and a standard deviation of 1, you're trying to find the area of what I put in orange. I mean, sorry, I said the wrong thing. Let me go again. So if you use inverse normal and you put area of 0.25, you're saying, okay, read it from left to right, right? Read it from left to right and give me the X value that is right here, see? And so you put in 0.25, so that means 25%. So it's reading from left to right until it reaches 25%. Now you know once it reaches 25%, you're going to be right at what we call Z1, which is the equivalent of 31.86, just in its standardized version. And so here you put the mean of 0 and the standard deviation of 1 because, surprise, standardizing it is very useful because it's a familiar space and you can plug in a mean of 0 and standard deviation of 1, which allows you to use all these different tools without a problem, right? And so if you go ahead and paste, and here it might make a little bit more sense, if you go ahead and paste, you end up with negative 0.674. So what this is saying is that your z1 value, let me erase this here, that's saying that this z1 value is negative 0.674, negative 0.674. Significant figures, we leave it like that. So this value here is negative 0.674. And so the z value that you're going to use is exactly this. So before we plug in over here, let's make a quick review because the concepts is very important that we understand them. See? So first, we started off by saying, okay, here's my normal distribution. This is what I know about it. You found Q1 and Q3 by using quick maths, knowing that that is basically how it works. See, Q3 minus Q1, you do 0.14 to the left, 0.14 to the right. You ended up with these key values. And now the problem that we faced is that these key values, as pretty as it looks, you don't have the standard deviation, so you can't use any of these tools. And so you say, let's go ahead and find its equivalent in the standardized version because it's a familiar space, and you know that the mean is 0. You know that the standardization is 1, and that allows you now to use all of these different tools. The tool that we picked was inverse normal because, surprise, we need to find the x value. And the only formula, the only formula or function on my calculator that I have for finding x values is inverse normal. So for inverse normal, you give an area, you give a probability, and you get an x value. And so we gave the probability of 25%, and we got the value negative 0.674. And so these are equivalents, right? And so the original 31.86, its standardized value is negative 0.674. And so now you can plug in over here. So negative 0.674, the z value, is going to equal its equivalent in x, which we said was 31.86, minus the mean, which we said was 32, divided by the standard deviation. And so here's another important point I sort of have to make. This mean and this standard deviation are the parameters of my original. Okay, these are the parameters of my original. Okay, don't be putting a mean of 0 and a standard deviation of 1 here. These are the parameters of your original. Okay, so that's also important for me to mention. Once you do this, though, you can finally get standard deviation alone. Because yes, this looks nasty. Yes, the procedure was kind of crazy, but look at this. What is your only variable? Your only variable is a standard deviation. So bada bim, bada boom, you can find the value of standard deviation without an issue here on out. See? So on the one hand, I would start off by multiplying standard deviation to both sides. That makes this goes away with this. You end up with negative 0.674 standard deviation equals, and up here it's going to be negative 0.14. If I do quick maths, that sounds correct. And so from here, you can divide both sides by negative 0.674, divide by negative 0.674. You end up with a standard deviation of negative 0.14 divided by negative 0.674, standard deviation of 0.207715, right? And if you consider three significant figures, you're going to count 1, 2, 3. See if you round it up or down, you round it up. So standard deviation, final answer is going to be 0.208. Make sure you put the right units, right? Ladies and gentlemen, that is the answer, as you can see over here, right? And that is how you do number 5. Now, as I said earlier, this exercise is kind of crazy in terms of concepts, in terms of understanding what the heck is going on. The biggest hint I can sort of try to remind you or leave really clear to you, okay, is that the reason you standardize it is because it's a familiar space and it allows you to use all these different tools, okay? It allows you to use all these different tools because the standardized version always has a mean of 0 and always has a standard deviation of 1. You just got to keep in mind that the z value, and this is what a lot of people just don't grasp very well, is that the z value is really just the equivalent of the original, right? And so the z value of negative 0.674, its equivalent is in 31.86 of the original, right? And so from a practical use, at least what we're interested in, you do this so that you can use the tools that are up here, see? Now, why would you do this like in real life? Imagine you're trying to find like, I don't know, dude, like you're comparing the height of men and the height of women in a certain class, right? And you want to see if like the height of one specific man, like in its own group, is it higher or lower than its own group in the women's, right? And so it's hard to compare the two heights because men tend to be taller. But what you can do is that you can standardize both of them, right? And see which one is higher in its own group, right? And so standardizing, and this is other like thing to keep in mind, like in real world, you standardize because it makes things very comparable. It makes it a familiar space, and it makes it all sort of like be more, it just makes it be more comparable, right? So if everything is in standardized values, it's easier to compare than if you have a bunch of different parameters going around, see? And so standardizing is useful for comparing. For our interests and purposes, it really boils down to, dude, you can use all these different formulas, and more importantly, you can use this guy right here, see? You can use this guy right here. If you ever need to find the standardized deviation, the standard deviation, sorry, at the AASL level, consider this equation a lot. Okay, I think it's probably the most useful one that you can consider. And that being said, enough blah blah by me. That is number 5, and I hope I helped. See you around.